Okay.
Yeah, no, we don't repeat the
Can you
introduction.
hear?
Okay.
But we can check if they hear.
I don't know. Can you check with them?
They can.
Now we can, okay, yes.
Okay. So I will talk about a unified control approach for a control approach design for idle vehicles, or typically more general for almost existing vehicles. This is my objective, but I will explain where we are live right now and what is missing and what is impossible to do. So I will try from the beginning, because this is a history of 25 years that I started with some people. Is Robert Mahoney. I started with this guy at the end of the 90s, and then with Pascal Morin at the beginning of 2000, and from 2006, typically with the Claude Sanson, is a guy. He's emeritus right now when working in my group. And the three guys here are PhD students working on this field. Mindy Kua is a researcher, CNS researcher, but he has a startup right now. Daniele Pucci is the director of the Department of Robotics at IIT in Genoa. And Thomas Lopez Oliveira is the last PhD student that I working on this field. And he just defended the thesis in December. So I will start with the motivation first, and then I talk with the proposed control approach for this kind of vehicles. You will see a lot of equations, but I will not spend time on the equation, just provide you the main idea behind them. So for the motivation, if you look to almost all existing vehicles, except cars and trucks, they are under-actuated. What does mean under-actuated? Whereas vehicle, if you look to the boat, is moving in a planar space, but has the 3 degrees of freedom, which are position X and Y, and the orientation theta on the plane. But it has only two control actions, which are the main thrust, the thrust and the main direction of the boat, and the rudder to orient the boat. The airplane is exactly similar to the boat, but is in 3D. You have one control action that move in the main axis, the main direction of the body, and three control torques that orient the vehicle. We have 6 degrees of freedom, but 4 control inputs. Here is a ducted fan, is a vehicle, a VTOL vehicle developed by a company in France. The name is Belton Technology. It is a vehicle that looks like a quad. The quad, I guess all people knows what the quad. You have 4 control inputs. Here is a bit the same. You have only one thrust, but there is 4 rudders under the duct here that can orient the vehicle. Similar to the quad, we have 4 thrusters, but the 4 thrusters provide just one collective thrust, which is the sum of all of them in the main direction of the body, and the others, they use it to orient the vehicle. For blimp or submarine, when you have a slender body, they works in the same way. The main difference is just here is in a plane, and the contact is with the fluid and with the air. This one is just the air. This one is the air, and this one is the water. So if you look to the models of the systems, are completely different. But we can't understand why they are different, because you have just an object moving in a fluid, and we have to model it in a simple way and try to design a controller. So in 2012, I did a course in Paris about drones, and one PhD student coming from the ONERA. ONERA is the national agency about aerospace and aeronautics. And he came up with a model, a complicated model that I will show you later. Anyway, I will start here. This is the model that he showed me for a quadrotor. And his supervisor said, this model is simple, but he has to complicate a bit more the model and then design a controller. Typically, people doing control, they don't need a model which is complicated. When you do something complicated, the controller will be also complicated, and we don't have a lot of margin to adjust something. what the control, the guys that are doing control theory, they need a model of the system which should be simple enough, but has the main features of the system, and then they design a controller. And I will talk about this later on. So what I would like a model that is valid for a large class of vehicles. I will talk about aerial vehicles because it's the main thing for today. And I will talk just in the last slide about submarines. The model should be useful for a vehicle using no structural lift. It is like helicopters, quadrotors. I mean, they don't have, the body don't provide any lift, okay, just from the thrusters lifts. And then they go to the vehicles with axis symmetry. It's like rockets and missiles. And from the first one to, from vehicle, they don't have lift, to another axis symmetric, they have lift. And then go to the fixed wing, which have more lift. And then I talk about vectorized thrust, fixed or vectorized. Fixed is airplanes. Vectorized is the new vehicles that we term convertible. That looks like the Harrier jet or the V-22 Osprey, the kind of vehicle that were developed in the end of the 50s or the beginning of the 60s. And the main idea is the way that we would like to solve a problem, not only for aerial vehicles, or also for marine and submarines. And encompassing also multiple flight modes. The first one is assisted mode, that we would like that we can control with a joystick, instead of controlling directly with the joystick the inputs of the vehicle. We provide just a desired velocity, for instance, and I control them like we control a car with a joystick. And we have the automatic control, which is asymptotic stabilization, either to a fixed point, if the vehicle is able to do it, or a desired trajectory. And the last one is stabilization around a geometric path, like what we do for vehicles with cars or airplanes. When you look to the literature, there is different control techniques. The first one is linear control techniques. Linear control techniques are really relevant for airliners, for instance, because when you look to the airliners, the main paths or trajectories they do in the airliners are trimming trajectories. And what does mean trimming trajectories? Are trajectories for which the velocity in the body fixed frame are constant, which is straight line, horizontal circle, or helix. For that, you can maintain velocity constant. When you have velocity constant, you can linearize the system. But they are not adapted for scale model systems. For scale model systems, they are sensitive to wind gusts, or when I said sensitive, it means that you can leave the region of linearization, means that we have to do something more robust, and they are not adapted for that. Are also not adapted for vehicles like air fighters. The air fighters, they don't look to a trimming trajectory. They have to be more aggressive to track a target and so on. And we have to do something for them. Nonlinear control techniques, there exist mainly two ways. The one which is position control, they term it also the outer loop. This is, were created at the beginning of the 90s. We can find them for air fighters, for instance, and also for quad and helicopters at the end of the 90s, and typically used in the community of robotics. For fixed wing is mainly ideas that coming from aeronautics, and they work with the air velocity control. Means they look to the velocity of the aircraft, and they control this with the magnitude and the angle of attack and side-slip angle. And there is also another technique, which is total energy. Total energy is another kind of technology that developed at the beginning of the 90s and also used in aeronautics, and they compose the system in longitude and lateral control. And there is the other one, the last one is the attitude control, which we term also the anal loop control. What I would like to say here is when I spent time on this field, and I found the people working in aeronautics, they have their own way to model the system. And even the physics, we can't get it quickly. There's a lot of books, and we have someone that he learned aeronautics in Israel, and they have different way to model the system, and the way is all the time linear, and there is no real explanation. They talk about angle of attack. They have to define 3 frames: inertial frame, body fixed frame, and the airframe or the wind frame. And they talk about angle of attack and different things. In robotics, they don't care. Anyway, roboticists, they know only the quads, typically, because they started around 2000. And their model is simple. I will show you why it is too simple, and also why it works. And there is a new vehicle. They term it convertible, which is instead of having fixed thrust, like here or here for the airplane, they have a thrust that they can change, vectorized. When it's vectorized, they would like to do something similar to the Swiss knife that works for hovering, that works for cruising flight, and not really the best solution, but this is right now, this is, we find maybe each week we have a new vehicles developed by different people around the world. And this is why also we have to develop a methodology that gather almost all of them. This is, I said, the model that one student came up and said he would like to solve it. I said, no, I can do nothing with this one. I can't understand it. I have to go back to the physics and try to understand simple things and what is the difference between all vehicles. So I need 2 frames, an inertial frame and a body fixed frame. This is the body fixed frame. Inertial frame is somewhere here, and the inertial is fixed, and the body is moving, is attached to the vehicle and moving with the vehicle. I define my states, which are the position, P, the velocity, and they have the acceleration, and they have the attitude, which is the orientation of the frame of the body with respect to the inertial frame. And the contrary inputs, I have a thrust in one direction. I put the airplane is I, direction I. For the helicopter, it should be K, and any other direction, but taking one of them. And I have the angular velocity, omega, and I put also the torque, gamma. Now I'm putting the torque in red just to specify all of these vehicles. I'm assuming that they are fully actuated for the orientation. If they are fully actuated, means they don't care about the control of omega. I will use omega as control input. And then from that, I just use a high gain and it works. The main problem should be only on the position and the orientation and the link between them. And VA is the velocity minus the velocity of the wind. So now when we look to the system modeling, I need equation, I need dynamics. The derivative of the position is the velocity. This is exact. The derivative of the momentum of the translation is the sum of the forces, which is the gravity, the thrust in the direction, the main direction of the body, and FA, which is all external forces. And we have the derivative of the orientation is also exact. This is kinematics. The main difference between all vehicles is lying here. This force can depend on the position, can depend on the velocity, can depend also on the orientation velocity, and even on the acceleration. When it depends on the acceleration, it means that we are talking about the added mass for a submarine or the blimp or something like that. But I'm not going deep on that. I will start just switching from one to another and simplify the problem. So the proposed strategy is what? We look to the position. When I have a car, I look to the trajectory that I have to follow. For instance, I go to on the highway, I try to take the middle of the highway or one of a corridor of the highway, and I follow it. This is my trajectory. And I decide the velocity with the desired orientation that try to be in the middle all the time. I can say this is my trajectory, I have P minus PR. And my PR, maybe there is a leader in front of me, I try to follow it. V reference and acceleration of reference. Okay, I define this error, position, and velocity. What I would like to find is the T and omega that stabilize the P tilde and P tilde dot to 0. Is okay? It's simple. Now, to do this, I look to the P tilde double dot is equal to acceleration minus the acceleration of reference. So I have to find xi that stabilize the things. But this is linear system. I can do a PD control. I can do a saturated PD control. I can do also a saturated PID. This is just the main AD that you can use, and then you can play with them. You have different tools, and all of tools exist in the linear system. Just here to provide just an AD. And the integral term is needed because when you talk about model, it's just an approximation of the physical system, means that we have to add the integral term anyway. Now, I would like to find the T and the omega that do the job, because right now I did nothing about it. I just defined the desired acceleration and the xi that do the job. So now I have to look to A and A desired, the A star, and put them equal to each other, and I will see what will happen. This is the acceleration is this coming from the model of the system. And I try to see when A is equal to A star, means that this equation is equal to 0, in order to define the T star, which is the first that I have to apply, and the desired attitude that I have to stabilize and provide to the pilot. When you look to this equation, I try to see when they are equal 0. I have different cases. The first case is when the drone has just a body drag, like a helicopter. They don't have a structural lift, okay? The lift comes just from the thrust, and the body looks like a spherical, and the only thing that you have is the force doesn't depend on the orientation. When the force doesn't depend on the orientation, I have I define F bar, which is equal to this term together. I will have just T star, I star is equal to F bar. Now, this is just a polar decomposition of F bar. This polar structure means that I can find the T star, which is just the norm of F bar, and the direction I star that I would like to stabilize, it should be just F bar over the norm of F bar. And this F bar doesn't depend on orientation because just the gravity, A star, which depends on the error between translation velocity and nothing more, and FA, which is just a drag, okay, and nothing else. And then for the G direction, I have to design it by adding an additional objective, okay. I can stabilize the direction of the quad, but when I stabilize the position, the orientation, the yaw, I have to find another objective to stabilize the full orientation. The problem become more complicated when we talk about missile-like vehicle. It's not a sphere. When you have a missile-like vehicle, you have something like my hand here, okay, is when this moving on the air, the VA is this, but the force is orthogonal, okay? When it's orthogonal means if I change my orientation, I change also the force. They are connected. They are not invariant like a sphere. Sphere is invariant to the orientation. Ellipsoid is not. So I have the drag and lift. People doing physics talk about drag and lift. The drag is the force dissipate the energy in the direction of the motion, and the lift is the force that I maintain the vehicle in the air, which is orthogonal to this VA. They have to decompose the force in two components in orthogonal frame. When you do the control, you can say this is make the problem impossible to solve. There's no explicit form because we have T A star is equal to F bar, A star, G star, and K star, and there is no closed form solution for that. How to solve the problem? I take the force, instead of decomposing it in lift and drag, I decompose it in another frame. One component is in direction of VA, and the other component is in direction of the thrust. When I do this decomposition, I have the force, I can write it like this. And we figure out there is two coefficients, which is C0 and C1, and they are coefficients which are constant. Allow me to do this. If I can do this, means that if I go back to the form that I explained before, and I use this form, this is my force, is this is the force. There's two terms here. One is the A star, in VA. I put the term in red, I put it with T star, because I can gather them. And I have this term here in blue, is the same F bar as before. And I have a T bar now, which is T star, similar to the one before, plus an additional term. And I have a new drag, which is F bar. It depends on C bar, 0, which is a coefficient which is constant. And then apply the same trick as before, as the sphere. And I go back to the same model from the sphere to missile or rocket shape. I get the same model, just playing a bit with the equations.
VA is the airspeed.
The VA is not the airspeed, it's the air velocity, is a vector. The norm is the airspeed.
Mm.
Now, in order to show you this is correct, because we spent time to publish this kind of papers, and the people from aeronautics said, no, it doesn't work like this. Unfortunately, it is hard to convince people, and we get data from NACA. And this is the data in blue is the real from the NASA, and the black one is the model that I showed you, with two coefficients C0 and C1, and it fits very well, except when we have a stall here, but the stall is another problem. But I just show you the main 80. When we try to do a control, you don't have exact model. You have approximate model. With the approximate model, you do a lot. Now I go to the airplane. How to model the airplane? The airplane, the other one, it was axis symmetric vehicle, and the symmetry is around the axis of the thrust. Now I'm using another axis symmetric vehicle, but it's not symmetric around. Look to the disk. I'm not using a disk. The disk is similar to the ellipsoid. Okay, but if I put the thrust in the direction in the plane of the disk, I create something similar to the airplane or an air fighter. If you look to the air fighter, they have small wings, and I can approximate it with a disk. And with the disk, I can get another model similar to what we did for the sphere, for the ellipsoid. And I have FA, I decompose it the same way. I have the C bar in direction of VA. I have something in direction of I, and I add something else in direction of G, because we have a side slip angle now that appear. And the C bar is the same as before. And I do the same computation, but I add another color, which is the green one. The green one is related to the other component that I have. And I gather with the same thing as before, but the green one is the additional thing that appears in the airplane. I have to put this equal 0. This equation equals 0 is a bit hard, but I can put this term equals 0 and this term equals 0. I can split them like this. If I split them like this is 0 and this is 0, and not the sum equals 0, I go back to the same way that the people in aeronautics are controlling the vehicle. But the thing is, putting G star is equal to the to VA cross I star. What does mean? Does mean G star here is orthogonal to VA, and this term is going to 0. If I do this, this is what they term bank to turn. An airplane can turn like this. To turn, they have to do this. Okay, or coordinated flight. This is what the people from aeronautics are doing. and you get the same thing as before, and you solve the problem. Now I'm complicating a bit the problem, going to the convertible vehicle. Convertible vehicles are vehicles that are able to do hovering and cruising like an airplane, and there is different. And I bought in my lab around 6 or 7 different kind of vehicles just to try them and test them. This is a few of them are here. I'm using the same idea as before, except here because I have a new degree of freedom, because the thrust here has 2 components, one direction I and one direction G. I take the force, as I said, that is one direction V and one direction. Anyway, I just decomposing the acceleration here using 2 terms. There is a D, one with the term C0 and the other one with the term C bar. All of this term doesn't depend on the rotation, and I do the same thing. I can compute the angle theta of the thrust based on I star and K star. This is the direction, desired direction of the altitude. And then doing this, if the orientation conversion to the desired one, I can ensure that I can get the xi as before, and the xi ensure that the desired p tilde and p tilde dot are going to 0. Okay. So now the problem is how to define the I star and K star, because it's not easy as the previous case. I have to add something else, another objective, which is, for instance, determine the angle of attack that minimize the thrust. This is one option. I can use the tilt depending on the air speed. Means if the airspeed is slow, I can take this kind of angle. More when I increase, I become like an airplane. Do it like with engineering thing or using optimization. Using optimization, you can see that when you stabilize the vehicle, it should be like this. Means that you have an angle of attack equal to 45 degrees, and the thrust is like this. Means that the tilt is 45 degrees, and the angle of attack 45 degrees. But even here, when you have small wind, what we have to do, what's the best solution, is not clear yet, but at least with the math that we are using, this is what we get. And now, okay, all the things are done. I have the T star, I have the orientation. What I have to do? I have to control the orientation. How to control the orientation now? I have the desired orientation. I compute the omega star, which is the desired velocity of the desired orientation velocity. And then I can define an omega d. The omega d is my control input right now. This is what I said before. I use this as control. In order to use it as control, I have to use the cross product between I and I star. And summing up all of this kind of vector, I can ensure that the orientation converges to orientation, desired orientation, exponentially and almost globally. And now I talk later on about the torque, but before that, people doing control, they took MATLAB simulation, and for the MATLAB, they take just the equation and they apply them. Here, what we are doing, we are trying to do finite element in order to see how it works with different kind of vehicles, and the model in order to be more realistic than just put in the dynamic equations and apply them directly. What we do, we take the airplane or any vehicle, and we do the finite element, we decompose in small pieces, even with disks or ellipsoid, and even for the control, we are using disks for the ruders and so on, because we can have analytic expressions for aerodynamical forces and so on. And we can do, and summing up all of those the contributions. This is how it looks to the force for one element. And then we sum up all of these things, and we do simulation with MATLAB, and we can see, or Scilab, and we can see how it works in simulation. This is how we decompose, for instance, an airplane. Is simple. Yeah, and for the control torque, as I said, since it's fully actuated, I don't need to know the gamma A, which is aerodynamical torques. I just apply a high gain and it works. This is the first step. And when we masterize things, you can try to make things a bit more specific to each one. I go first to the simulations, because it's nice to see how it works for the simulation. And maybe you can get the point from it. Oops. Yeah. This is the trajectory. I don't remember now which one is. I guess it's the red. The desired, no. The desired is in yellow, and the real one, the actual one, is in red. This is in different planes, X, Y, and Y, Z, and X, Z. The green one here is the magnitude of the thrust, what the vehicle has to produce in order to realize this trajectory. I just go back a bit here in order to show you this is, in this trajectory, you see that the vehicle has to provide a lot of thrust, okay? For the helicopter, you have to spend a lot of energy to realize this kind of trajectory. And they are doing looping, okay? Now, the same trajectory with the annular wing, which is axis symmetric, is like the missile line. We added just an annular wing in order to have more lift, okay? And we see the thrust here is lower than the previous case, okay? Because we have some lift which is helpful. Not at the end, because at the end when you stabilize, we have to compensate for the gravity. But you see at least the trajectory, how it works. And finally, the airplane. Just to convince you, even in simulation, it looks like the motion of the airplane, and then I will show you the experiments. Because we spent time first in the simulation part. This is how it works for the airplane, and you see the bank to turn, okay? When you try to turn, you have to bank a bit to make the G star orthogonal to the direction of VA. And to make, side ship angle equals 0, in a sense. And you see the magnitude of the thrust is smaller. Okay. Now we'll show you the first experiment on, for this work. Is a real airplane. I was cheating here because I was not allowed to do this kind of experiment. This is, you see, this is a lot of houses here and there. And we said we are playing a bit with an airplane and there is no problem, but we did it in automatic fashion. But this is the trajectory. The desired one is in black, and the red is the actual. This is, we are doing like a trimming trajectory first. You see a straight line, an arc of circle. And then when we are climbing, it's not exactly a trim because we are changing different things for the climbing. And then I will do an arc of circle, which is inclined circle, when this is not a trim at all. You see it later on, but you see the vehicle anyway, above. Yeah, if I ask for authorization, I will never do things. They have to play with the rules, and yeah, you see the inclined circle for this kind of vehicle. I will show you another experiment. This is, there are different small experiments because this is with the convertible vehicles. In convertible vehicles, we have different kind of convertible vehicles. This is one of them. Yeah, we have different kind of actuation. Here we are looking to the tilt. and we are controlling the tilt in the transition phase. And here is the airspeed with respect to the speed. You are controlling the speed, not the airspeed. But what you measure is the airspeed with the pitot tube. And yeah, we did different kind of experiments. We did with this one until 150 kilometers per hour. And with another smaller, we did 120 kilometers per hour. We had a lot of crashes for sure. You see, it's a nice place anyway. I will show you other pieces of the experiment. Yeah, this is following waypoints, but there is a lot of wind. Yeah, going from one point to another with the convertible vehicle and changing also the speed. Changing the speed means that they have to change the mode of the vehicle. Okay, sometimes it looks like an airplane, sometimes like a quad, and with a lot of perturbation. And you see here the trajectory is followed very well. And when we arrive here, you see an overshoot because there is a lot of wind, and we have to manage this kind. But this is just the first result that we got in December, and we have to work a bit and to improve a bit. And we're still working on this kind of vehicle. Here you see a lot of a big overshoot because there is a lot of wind. I have different kind of vehicles. I will show you some of them. This is another one. Unfortunately, we have a motor which is broken. Yeah, with this one, we did 120 kilometers per hour. It's very small, but yeah, it doesn't exist anymore on the market. This one we have 2 or 3 of them. We already crashed one. Yeah, but they are not expensive. I mean, each vehicle is around 1,000 euros. They're big, but it's Chinese vehicles. They're not really expensive. Okay, it's good for research in a sense. Yeah, I mean, I will talk a bit the first lesson that we get from all of this kind of vehicle. Yeah, the proposed methodology that I talk about, because I have to normalize, I have to divide, the thrust should be the F bar over the norm of F, for instance. This works for all vehicles, they have gravity. When you have gravity, there's no problem. The force is not crossing zero in a sense, and we can avoid crossing zero. And we can do this in a cascade way. We have to control the position, and then you get the desired attitude, and then you control the attitude. It works like this for almost all existing vehicles, except, and even for boats when we are moving, or slender underwater vehicles. We did the theory for that, but the decomposition is different. I'm not decomposing the force, I'm decomposing the momentum on different axes. Here they did the force. For the submarines is the momentum because you have the added mass and things like that. But all of these things doesn't work when we don't have the gravity. When we have a neutral submarine, this doesn't work because the force can cross zero. And you can't have a cascaded system. You should have 2 subsystems in parallel. It's like stabilizing a car, for instance, and you know that the stabilization of the car is not, linearization is not controllable, and we have to do something else. This is what we did recently, which is for a company. We have an under-actuated system. I will show you how it works. The system is under-actuated. They don't have any action on the yaw axis. And the system, we can stabilize it using an older tool, which is based on exploiting the Lee brackets, because we look just to the direction that we have as control, and with the Lee brackets we built orders, and from that we lift the system in another group, and you do the control on this group, and then you project down again to control the system. And what we get at the end something like doing maneuvers. And this looks like doing a parking for a car, for instance, is a bit similar. The problem here that you see here is a bit complicated because the system is not observable and is not controllable. But putting all together, we can stabilize and we can observe. Because of the way that is done, the theory match very well with the practice in that case. And this is the end of my talk.
Okay, thanks. Now we can